Fluorine. Even the name sounds dangerous. It hisses like a lit fuse, crackles with untamed energy. And for good reason. This element is not for the faint of heart. It's the smallest, lightest halogen, a true featherweight with a heavyweight punch. In the world of elements, fluorine reigns supreme as the most reactive. It forms bonds with almost everything, a promiscuous partner in the dance of chemistry. Drop a chunk of fluorine in water, boom, instant explosion. Even noble gases, those aloof loners of the periodic table, can't resist fluorine's charms. But don't let its ferocious reputation fool you. Fluorine, despite its volatile nature, plays a crucial role in our lives. From strengthening our teeth to powering nuclear reactors, this element is a true paradox, a force of nature both destructive and indispensable. So buckle up, dear reader, as we delve into the fascinating and sometimes explosive world of fluorine, the reactive rebel of the periodic table. Imagine a grand palace, each room housing a different element. This is the periodic table, a majestic mansion of matter. Our fiery protagonist, fluorine, resides on the top floor, in a room with a spectacular view, the halogen family suite. Number 9 on the periodic table, fluorine sits comfortably between oxygen and neon. Its lightweight nature, with an atomic weight of just 19, belies its incredible reactivity. This small stature, however, is key to its power. Fluorine's electrons, those tiny particles zipping around the atom's core, are held in a tight grip. This makes them desperate to pair up with electrons from other elements, leading to the formation of strong, stable bonds. The result? An element so eager to react, it makes even the most cautious chemist nervous. The tale of fluorine's discovery is not one of serendipitous accidents or sudden flashes of brilliance. It's a story of persistence, of trial and error, and unfortunately, of significant sacrifice. For decades, this elusive element remained hidden, its true nature a mystery. Early chemists suspected its existence, observing its effects without ever isolating the pure element. They knew something reactive lurked in the shadows, something that etched glass and ignited combustible materials with ferocious speed. It wasn't until 1886 that French chemist Henri Moissan finally wrestled fluorine into submission. His victory came at a cost, however. The experiment was fraught with danger, and many before him had suffered severe injuries, even death, attempting to isolate this volatile element. Moissan himself didn't escape unscathed, bearing the scars of his triumph for the rest of his life. What makes fluorine such a reactive rebel? The answer lies in its atomic structure. Picture this: a tiny atom, its nucleus a cluster of protons and neutrons, orbited by a cloud of electrons. These electrons, negatively charged particles, are the key players in chemical reactions. Fluorine has 7 electrons in its outermost shell, just one shy of a full house. This insatiable hunger for that final electron drives its reactivity. It desperately seeks out other atoms, eager to snatch an electron and complete its octet, a stable arrangement coveted by all elements. This electron thievery is what makes fluorine so reactive. It forms strong bonds with almost every other element on the periodic table, often with explosive results. Even seemingly inert substances like glass and noble gases can't resist fluorine's seductive pull. Section 5. Taming the wild element. Practical applications of fluorine. For an element so demonstrably dangerous, fluorine has found its way into a surprising number of everyday applications. The key lies in harnessing its reactivity, taming its wild nature for our benefit. By carefully controlling the conditions, chemists have managed to utilize fluorine's power for a wide range of purposes. One of its most well-known uses is in the production of uranium hexafluoride, a crucial component in the nuclear industry. This volatile compound allows for the enrichment of uranium, a process essential for nuclear power generation, and, unfortunately, nuclear weapons. Fluorine also plays a critical role in the production of Teflon, that ubiquitous non-stick coating found on cookware and countless other products. This remarkable material, chemically known as polytetrafluoroethylene, or PTFE, owes its slippery properties to the strong carbon-fluorine bonds that repel water and oil. Section 6. Fluorine in our homes, from toothpaste to Teflon. It might surprise you to learn that you encounter fluorine every single day. This seemingly exotic element plays a surprisingly intimate role in our daily lives, often in ways we barely even notice. Take toothpaste, for example. That minty fresh paste responsible for your pearly whites contains fluoride, a compound derived from fluorine. This mineral strengthens tooth enamel, making it more resistant to decay caused by sugary snacks and acidic beverages. Then there's Teflon, that miracle material that prevents your eggs from sticking to the pan. This non-stick wonder is a polymer of tetrafluoroethylene, a compound made up of carbon and, you guessed it, fluorine. Its resistance to heat and chemicals makes it ideal for a wide range of applications, from cookware to waterproof clothing. While fluorine might be best known for its domestic applications, its role in the nuclear industry is equally significant, albeit far less visible. This reactive element plays a crucial role in the complex processes that drive nuclear power plants and, controversially, nuclear weapons. Uranium, the fuel that powers nuclear reactors, exists in nature in a form that's not directly usable. It needs to be enriched, a process that increases the concentration of the uranium-235 isotope, the one capable of sustaining a nuclear chain reaction. This is where fluorine comes in. It's used to create uranium hexafluoride, a compound that's gaseous at relatively low temperatures. This gas is then spun at high speeds in centrifuges, separating the lighter uranium-235 from its heavier counterpart, uranium-238. The enriched uranium can then be used to fuel nuclear reactors. Fluorine, a true enigma of an element. It's a force of nature capable of both destruction and creation, a double-edged sword that demands respect and caution. Its benefits are undeniable, but its potential for harm is equally real. On the one hand, fluorine strengthens our teeth, prevents cavities, and ensures our morning eggs slide effortlessly off the pan. It powers nuclear reactors, providing clean energy to millions, and enables the production of life-saving pharmaceuticals. But this reactive element also has a darker side. It's a key component in the production of sarin gas, a deadly nerve agent, and plays a crucial role in the enrichment of uranium for nuclear weapons. Its industrial uses can lead to environmental contamination, posing risks to human health and ecosystems. As with many elements, the story of fluorine is not without its environmental implications. While naturally occurring in minerals and even trace amounts in water, it's the industrial use of fluorine that raises concerns about its impact on our planet. The production of fluorochemicals, those versatile compounds found in everything from non-stick cookware to firefighting foam, can release harmful byproducts into the environment. These substances, known as PFAS, per- and polyfluoroalkyl substances, are persistent, meaning they don't break down easily in the environment and can accumulate in water sources and soil. Exposure to high levels of PFAS has been linked to health problems in both humans and animals. This has led to increased scrutiny of industries that use fluorine, with calls for stricter regulations and the development of more environmentally friendly alternatives. Despite its inherent dangers and environmental concerns, the future of fluorine remains bright. Chemists and researchers continue to explore its unique properties, seeking to unlock its full potential while mitigating its risks. One promising area of research focuses on developing new, more sustainable methods for producing fluorochemicals, reducing their environmental impact. Scientists are also exploring the use of fluorine in advanced materials, such as high-performance polymers and energy storage devices. In the medical field, fluorine is playing an increasingly important role in drug development. Its ability to form strong bonds with carbon makes it an ideal candidate for creating new pharmaceuticals, including those targeting cancer and other diseases. As our understanding of this reactive rebel deepens, we can expect to see even more innovative applications of fluorine, harnessing its power for the betterment of humanity while minimizing its potential for harm.